Alright, so this is the last section for the entire semester other than some reviews. So let me, before I start lecturing on the section, maybe introduce a new concept, the concept that we're going to deal with in this section. In this section, we're finding the area between two curves and some values of x. And let me just make up a generic problem to help introduce the material. So I'm going to create two functions. I'm going to go let my first function, y sub 1, equal just the number 5. And let y2 equal the number 1. And I'll say find the area of the region bounded by the graphs of y1 and y2 over the interval, and I'll write it with x's so it's going to be obvious that it's x's, over the interval about 3 is less than or equal to x is less than or equal to 6. So I'm going to do this pictorially. I'm going to draw a graph to explain to you what I want to find visually, and then I'll do this using calculus in my calculator. So visually what I'm asked to do is, well, to see visually what I want to do, I'm going to have to sketch some graphs. And the graph of y1 equal to 5, when an equation only has a y and doesn't have an x, then its graph turns into a horizontal line. So the equation y1 equal to 5 has this graph. It's just a horizontal line that goes through 5 on the y-axis. The equation y2 equal to 1, again, that equation only doesn't have an x, so it's a horizontal line because it only has a y. So these are the functions that I've brought up. And now, specifically, I want to look at the area between the graphs between x equal to 3 and x equal to 6. Let me draw those in. There's x equal to 3, and here's x equal to 6. So the area that I want to find is this area. And generally, I can't find areas that easily when I have a graph staring at me, but this is one of the rare times that I can find the area pretty easy because this is just a rectangle. If I know the height and the length and the width of the rectangle, I can find my area. So this length right here goes from y equal to 1 to y equal to 1 to y equal to 5. So this length is 1, 2, 3, 4. So this side of the rectangle has a length of 4. And the bottom goes from x equal to 3 to 4, 5, 6. It has a length of 3. So the area is 12, square units, I guess. Units squared might be nice, but we usually don't put the units squared on our answer. So that would be how to do a problem to find the area between two curves and between two values of x visually. It turns out that we can use calculus to find this same area, and it's really easy. To use calculus to find an area between two curves, you're just going to integrate or do the antiderivative over the values of x that are given. So this is I'm going to say x1 and x2 to represent the values of x. So to find a shaded area over a given x interval, we just have to integrate by subtracting the top function minus the bottom function over the interval that's given, dx. So to do this problem, to get this area of 12, what I'd have to integrate is I'd have to integrate the top function the top function y1, which is 5, minus the bottom function y2, which is 1, over the interval that's prescribed from x equal to 3 to x equal to 6. I'm going to combine like terms in there, and this is going to come out to be the integral from 3 to 6 of 4 dx. The integral of 4 is just going to be 4x, but I have to evaluate it from 3 to 6. So I'm going to go 4 times 6 minus 4 times 3, which is going to be 24 minus 12, which is 12, which is exactly the same number that I got. So to find an area bounded by the graphs of two functions and two values of x, we just have to integrate the top function minus the bottom function. In the last section, we had to make a big deal on whether a graph was above or below the x-axis. It turns out not to matter in this case, because when you're subtracting, it kind of negates that negative area. Let me just do another version of this problem just to show you that it's not going to matter if one function's above the x-axis and another's below the x-axis. So I'm going to do the same sort of thing. I'm going to let y1 equal to 5, and now instead of making y2 equal to a positive number, I'm going to make it a negative number, and then I'm going to write essentially the same question, except I'll probably abbreviate it. So I must say find the area of the region bounded by the graphs of y1 and y2 over the interval 3 is less than or equal to x is less than or equal to 6. I'll do this graphically again. So the top function still is missing an x, so it's a horizontal line. It's just a y equals, and it goes through 5 on the y-axis. The bottom function also is missing an x. It goes through -1 on the y-axis, and it's a horizontal line. When equations don't have x's, and they only have y's, they're horizontal lines. And now I want to go between x equal to 3 and x equal to 6. So in this case, the region that I'm worried about goes above and below the x-axis. And when you're dealing with just one function and finding the area between one graph and the x-axis, you have to worry about when you dip below the x-axis. But in this section, we won't. When you're finding the area between two curves, because you're subtracting, it kind of winds up adding this negative. Because you're subtracting a negative, it winds up adding it. So let me go ahead and figure out what this is by hand. So this is a rectangle again. It has a height of 1, 2, 3, 4, 5, 6, or a length of 6. So from the bottom to the top, the rectangle is 6 units. And going this way, again, it's 1, 2, 3 units. So the area that I have shaded here is going to be 18 units squared. To find that 18 using calculus, I do the same thing. I'm going to integrate from 3 to 6, the top function, which is 5, minus the bottom function, which is -1, dx. And let me simplify this. This double negative turns into a 5 plus 1, which gives me a 6 dx. A 6 dx evaluated from 3 to 6. The integral of 6 is 6x. So to do this, I just have to take the function 6x and evaluate it at 3 and 6 and subtract. So this is going to be 6 times 6 minus 6 times 3. 6 times 6 is 36. 6 times 3 is 18. 36 minus 18 is exactly the same area. So the only thing that we're going to do in this entire section is find the areas between curves. The first few problems are given to us as graphs, and we'll be able to use our calculator on those problems. And then we'll be given some problems that are just like these, where we'll be given two functions and values of x and some values of x's. And then we'll get into something that's a little bit harder, that takes a little bit of algebra to get started, but I don't need to talk about that just yet. So let me get into the section, and for every problem in this section, I'm going to use this strategy to find the area between two curves over a specific interval of x's. So I just need to identify both the top and the bottom function. So I'm going to do number 2, and then after I do number 2, you should be able to do number 1. Here's my y1. My y1 is the function that's y1 equal to 6. So it's just horizontal line that goes through 6. And my y2 is the x squared plus 2 parabola. And I'm asking you to find the shaded area. And in order to find the shaded area, I need to be able to integrate the top function minus the bottom function. The top function is the 6. The bottom function over the shaded area is x squared plus 2. So I'm going to integrate 6 minus, and because I'm subtracting a binomial, I need a parentheses. And then I need the dx. It probably would be nice if I did this, but if I didn't have the brackets, it's hardly that big of a deal. I need x values, so I wasn't given x values here. Well, this graph starts, the shading starts right there at x equal to -2. Hopefully you could read that -2. So that's going to be the beginning of my integral. And this shading ends at x equal to 2. That's going to be the end of my integral. As I read this, the function whose graph is represented by the dashed should say line. I think on every problem, I forgot to write line after dashed. And the function whose graph is represented by the solid line is the y2. So to get this area, I just simply integrate this. If I was doing this by hand, I would definitely simplify this a little bit. So I want to do the integral from -2 to 2 of 6 minus x squared minus 2. I need the dx. Usually, if you're integrating a polynomial, you put it in a parentheses. So I want to integrate from -2 to 2 of -x squared plus 4 dx. And for problems 1 through 10, we'll be able to use our calculator to find the shaded area. Once we get out of the problems that supply a graph, then we have to do them by hand. So let me do this. I'll live with decimal answers for 1 through 10, just to get you used to just getting the concept started. So to do problem 2, I'm going to hit y equals, clear out the junk that's in there, and do -x squared plus 4 for my graph. And then it's not going to look like this so much, but it's, heck, it's okay. So I'm going to enter, so, gosh, visually it's not that appealing now, because now it doesn't look like this, but I can still get the answer. I'll show you in a second by hand. So when I do algebra and subtract the functions, the graph that I get has the same area as the shaded region, but it looks different than the shaded region. And let me do this by hand in a second, just to show you. I don't even know what I could do by hand to make this better. but I'm going to try. So I think that says 10 point. I'm rounding to 2 decimals. So for each of the problems between 1 and 10, it's going to be okay to do the integrating on your calculator. To do the integrating on your calculator, you need to take the two functions and subtract them down to one function. And when you do that, it destroys the graph. I don't see the graph of either function. If there was another way to do it that you could keep the graphs, let me show you how to do that. So if I wanted to enter the function 6, I can find the area beneath the graph. I could find this area by integrating that. So if I wanted to do that and graph that, I can find the area that I just shaded in pink between -2 and 2 by going second calc, option 7, lower limit -2, upper limit 2, and it gives me this big area is 24 square units. And next I'm going to find the area that is beneath the parabola. I'm going to do that in blue. And to do that area, I'm going to have to enter that function, clear, so x squared plus 2, graph it, and there's the parabola that I have there. And I'm going to, again, second calc, integrate between -2 and 2, and it gives me the lower, or the smaller area, or the lower area, which I have in blue, is 13.33. If I subtract those two areas, I'm going to get the 10.67. So if I go to my main screen now and go 24, the area underneath the y equal to 6, minus the area underneath the parabola x squared plus 2, I get the shaded area, or I get the area that I'm trying to find, the area that was initially shaded, which is that area. So I could, if I want to, use both functions and find the areas that I need to, and then subtract to get the final answer. But that takes a lot more work, because then I had to do one integration for the first I didn't do an integration for the top function, an integration for the bottom function, and then I had to subtract them. The alternative was to actually subtract the functions, and when I actually subtract the functions and integrate, it destroys the graph. The graph doesn't look the same anymore, but the area comes out to be the same. And that's all I'm worried about, is what the area is, and I don't necessarily care exactly what picture my calculator is showing me when I go to do the first 10 problems. So from problems 1 through 10, what we're going to do is figure out the equation of the top function, the bottom function, subtract them, integrate over the values of x's that are kind of prescribed by the drawing. And the drawing on my calculator, because I'm only going to be integrating one function, will have the same area as if you kept the original functions, calculated the two areas separately, and subtracted them. It's just quicker. So hopefully that wasn't so bad. We'll do a lot of these, so hopefully it goes eventually smoothly. So here's problem 1. You can do this on your calculator. This dashed line has the equation, we'll say y1 equal to 4. And then the parabola has the equation, y2 equal to x squared. It hardly matters what I call them, because I'm going to subtract the top function by the bottom function. The y1 is the top function. The y2 is my bottom. It doesn't matter if I call them y's or f's and g's. And then I have to decide where I'm integrating from, and it's the same -2 to 2, because the shaded area, it starts at x equal to -2, it ends at x equal to 2. So you're going to integrate to do problem 1 from -2 to 2, the top function, which is 4, minus the bottom function, which is x squared, dx. If you entered that on your calculator, you'll get exactly this shaded area, but the graph isn't going to look the same, but it doesn't matter. Alright, so when I go to do problem 4, again, all these, if you read these, it might drive you crazy, that the function whose graph is represented by the dashed line is negative x squared plus 18. The function whose graph is represented by the solid line is x squared. So I have to figure out the top and the bottom function. So that's the x squared, and that's the bottom function. The dashed line is the top function. And I'm always, when I'm finding a shaded areas, I'm integrating the top function minus the bottom function over the prescribed range of x's. And this graph, the shading starts here at x equal to negative 3, and it ends at x equal to 3. So to find out this shaded area, I'm going to integrate from negative 3 to 3, the top function, negative x squared plus 18, minus the bottom function, minus x squared dx. Because the bottom function was just a monomial, it doesn't have to go in a parentheses. If you put the x squared in a parentheses, you'd wind up just getting a negative x squared anyways. These two negative x squareds don't cancel. This is a negative 1x squared and a negative 1x squared. They combine to be a negative 2x squared. So in a second, I'm going to integrate from negative 3 to 3. The function I'm going to integrate is negative 2x squared plus 18 dx. I'm going to get a function that has the same area as this region that doesn't look like this region. So let me try to just do that real quickly. So y equals clear negative 2x squared plus 18. Graph it. My window doesn't go high enough to see everything, but I still can get the answer. Second calc, lower limit negative 3, upper limit 3. And my answer, the area that's represented in this problem, would be 72 square units. And I usually just write 72 without the units here. Alright, so your problem 3 should be real similar. So the top function is the dash function, so the f of x is your top function. The bottom function is the g of x. So you're going to integrate top minus bottom, and it's hard to read this a little bit, so it starts at x equal to negative 2, the shading. It ends at x equal to positive 2, the shading. So you're going to integrate from negative 2 to 2, the top function minus the bottom function dx. And that will give you that shaded area, even though the picture is going to be a little bit different. And again, I have all these dash lines that need to be added in there, but yeah, they're good enough the way they are. So you might be able to get a few problems done without me, but then you might run into a trick on, well, you're not even going to see the problem that it's a trick unless you have it printed out in front of you. But there's some tricks to these, and we haven't got to it yet. All right, so for my graph right here, I'm only integrating between x equal to negative 1 and x equal to 2, because that's where the shading is gone, between x equal to negative 1 and x equal to 2. The top function is the dashed function, and the dashed line is it's actually dash curve, I guess, is the f of x function. So I'm going to integrate from negative 1 to 2. Negative 1 is the x coordinate of where the shading starts. 2 is the x coordinate where the shading stops. The top function, negative x squared plus 7, minus the bottom function, negative x plus 3. When the bottom function isn't a monomial, it has to go in a parentheses. You need the dx. If I just wrote it like this with a dx, I wouldn't take points off, but now it looks like the dx doesn't apply to everything. It would be nicer if I bracketed this stuff to make sure that everything is being integrated, I guess. So, doing exactly what I did for the first two problems, found the values of x where the shading starts and stops, puts those on my integral sign. Top function is the dash function, bottom function is the solid line. And now I'm going to simplify this. Integral from negative 1 to 2 of negative x squared plus 7, minus a minus x turns into a plus x, and a plus 3 turns into a minus 3 dx. Simplify that a little bit more. I get the integral from negative 1 to 2 of negative x squared plus x, and 7 minus 3 is plus 4 dx. I'm going to graph that and do it on my calculator. So y equals clear negative x squared plus x plus 4, graph it, second calc 7, lower limit negative 1, upper limit 2. My answer, the shaded area that's given in the original problem, has an area of 10.5 square units. Even though the graph of my work looks different than the graph of the work here, it's still the same answer, and it's a lot easier to subtract and integrate one function rather than doing one integral with the top function, a second integral with the bottom function, and subtracting them. So my graphs won't match up perfectly to the graph here, but the answer will match up perfectly. Okay, just in case you can't see for your number 5, this graph, the shading starts at x equal to negative 1, and the shading ends at x equal to 2. The top function is the dashed line, which is negative x squared plus 11. The bottom function is the solid line, which is negative x plus 4. So you're just going to do the proper integration there to get your answer. If you move down and try to do 7 because you have the problems printed out, you might get stuck. Because in problems 8 and 7, the graphs cross over each other. And I'm going to have to do 2 separate integrals because here the dashed line is the square root of x, and in the first little region the dashed line is on top. So I'm going to have to do that area where the dashed line is on top separate from this area where the solid line's on top. So if the graphs cross in the area, in the values of x's that you're having to integrate over, you're going to have to do 2 integrals. So I'm going to have to integrate here from 0 to 1, the top function, which is the square root of x, minus the bottom function, which is x cubed. And then from 1 to 2, I'm going to integrate the top function, which is x cubed, minus the bottom function, which is the square root of x. So I'm going to have to do 2 separate integrals. So the blue region will be the integral from 0 to 1. The top function is the square root of x. The bottom function is x cubed dx. And then I'm going to have to do the pink region. And in the pink region, the top function now is the solid line, which is x cubed. The bottom function now is the dashed function, which is the square root of x. And that's between x equal to 1 and 2. I'm going to get a number for each one of these, and I'm going to add them together. So the nice thing is I only have to, well, oh no, I do have to enter the functions twice. I have to do 2 separate, completely different works on my calculator. So top integral, y equals clear second square root of x, close out the parentheses, oh, I can't even see it, and then minus x up arrow cubed, and I'm going to integrate that from 0 to 1. So get the graph done, second calc, number 7, 0, enter, 1, enter, and that area is I'll say 0.42. And then for the second area, I have cubed minus second square root of x, graph it, and then second integrate from 1 to 2. You get 2.53. The total shaded area is the sum of those two. So I'm going to go back to my main screen and go 2.53 plus 0.42. And my answer, the shaded area that was initially given to me, is 2.95 units squared. So the only trick we really have in this grouping of problems is that the functions can cross, and at part of the window, one function's on top, and the other part of the region, the other function's on top. So we just have to be cognizant of that. Your problem for 7 is almost the same. You can see that the dashed line, the square root of x, is on top between x equal to 0 and x equal to 1. And then it flips, then after x equal to 1 up to where the shading ends at x equal to 2, the solid line is on top. So you're going to have to integrate from 0 to 1, the top function square root of x minus the bottom function x squared. And then you're going to have to integrate from 1 to 2, the top function x squared minus the bottom function square root of x. And I have to do these as two separate activities on my calculator. Again, the graphs on my calculator don't match the graphs when I do these subtracting, but the area is correct still. Alright, I'm not sure if we get a hiccup in the video here. I started doing number 10 because that was my even problem to do, and then it was just messed up. Somehow the graphs of the functions didn't match the graphs of that were on my paper, so I decided I would just do number 9 with you and skip number 10. I'll fix number 10 and put it back in my web page, but we don't need to do number 10. Let's just work on number 9. So for number 9, the functions cross again. So the dashed line is 2 minus x, the solid line is x cubed plus 3x squared, and so at first, let me do it in blue, the dashed line is on top. Between x equal to 0 and the x coordinate of where these two lines are on top, or the dashed line is on top, I have to integrate the 2 minus x function minus the x cubed plus 3x squared function. This problem gives an extra twist, and that extra twist is I don't know where the two graphs intersect, and I said use the intersect feature on your calculator to estimate the points of intersection when needed. So I need to get the x coordinate of this point to know where to stop integrating this for that area and where to start integrating for this area, because the next area I'm going to do is going to be that little small area right here. In that region, the solid line, the g function, is on top. That starts at that value of x where the points intersect and ends at x equal to 1. And that's going to be the g function minus the f function. So just like in problems 8 and 7, the graphs cross, and when the graphs cross, I have to do two separate integrations. It's always the top minus the bottom, and because it flips where they intersect, which graph is top and which graph is bottom, I have two integrations to do, neither of which I have completely written out because I don't know where the graphs intersect. To find where the graphs intersect, I'm going to, on my calculator, enter into y1 the 2 minus x function, and in y2 the x up arrow 3 plus 3x squared function. I'm going to graph them and get a graph that looks just like my graph without the shading. And now I'm going to go second and then calc, use the intersect feature, which is option 5. And for the intersect feature, you can be lazy. You can just start tracing and get as close as you can to the point where they intersect and just hit enter 3 times. So enter, 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 and it'll give you its best guess. I'm going to round that to 0.62. So the x coordinate of where these two lines or graphs cross is 0.62. And I don't even need the y coordinate of that point because the y coordinates aren't an issue when I'm integrating. So to finish up what I'm writing here, I'm going to integrate the first function between 0 and 0.62. The second function I'm going to integrate between 0.62 and 1. If I want to be lazy, I don't have to simplify these functions. If I enter it just like it's written, my calculator doesn't mind if it's an unsimplified version. So let me be lazy with problem 9 and go y equals clear, clear. And I'm going to enter the function y equals 2 minus x minus parentheses x up arrow 3 plus 3x squared. That just saved me the grunge of doing the algebra to combine like terms. So that will have the same graph as if I dumped out the parentheses and combined like terms. So I'm going to graph it. I'm going to find the first area by going second calc, going down to option 7, integrating from 0 to 0.62. And I get 0.77 for this area. And then I'm going to move down and do the second area. To do the second area, I have to enter the function differently. I'm going to enter x. Oh gosh. Let me make sure I didn't just mess up, because I don't know what I just did. Let me redo that first part. I'm not sure if I made a mistake or not. So let me just redoing this part 1. I don't think I did, but just in case I did. Second calc, 0, enter, 0.62, enter. Did that one fine. Now I'll move on to the second part. Clear out that function and do x up arrow 3 plus 3x squared minus parentheses 2 minus x. Graph it. Again, doesn't give me the same graph as is presented to me in the problem, but it's okay. I don't need to have the same graph to get the area. So 0.62 to 1. This area is 0.52. Now I'm just going to add the areas together to get my answer. So my answer for problem 9 is going to be something. I could write square units, but it's going to be the sum of these two. So I'm just going to go to my main screen and go 0.77 plus 0.52, and I get 1.29 square units. And again, I haven't been putting the units squared, so it's completely okay if you don't. All right, now we're going to get into the problems where we're going to have to do our work by hand. So we got 10 freebie problems, and then we have about 15 problems. Well, it goes up to like 32, so 15 or so problems of pure calculus.